talking about actually one of my favorite topics, and one which is like I find really interesting. We're going to be talking about nonlinear analysis. So we've been, if you're unaware, we've been working with linear models. So what that means is if you have a stress strain curve, you're in the linear region. So what do we think a nonlinear model is? Any thoughts?
Yielding?
Yes, after yielding. What happens after yielding? And so if I go to a stress strain curve, this is what a stress strain curve looks like. You guys probably are familiar with this from AME 204. What we've been looking at when we've been analyzing parts is this linear region, right? So what kind of happens there? But surprise, if you go past your yield strength, everything doesn't automatically just break. It will soon, but it does. There is some interesting behavior that happens once you reach your nonlinear region. So yeah, strain hardening and necking, we'll see this in action. I think it's going to be pretty cool. But yeah, so this is sort of what we're going to be focusing on today. And so yeah, ANSYS can do nonlinear. It's still your same static structural, but you have to do a few things differently. So yeah, these are just previous runs I set up, but we're going to start, fully from fresh. So I'm just going to make the model real quick. All right, it's a simple model. We're kind of just more interested in looking at how the stress strain or how it behaves nonlinearly. But are there any questions as well from any of the previous ANSYS tutorial or any questions you guys have? Okay, we're just going to make a rectangular beam, similar to, very common to what we've been doing. Another pro tip, I'm sure I've mentioned this a lot, but I definitely recommend working in imperial. I think it's usually better unless you're working with thermal analysis. So we're just going to make a 6-inch beam here, 1-inch width, and we're going to just put a hole in the center for something like that. And then we're going to extrude this like 1/4 inch. I know SpaceClaim is not the ideal CAD. Okay, now onto the interesting stuff. So if we double click engineering data, you guys have been defining engineering data. You might realize that okay, all the stuff we've been defining so far are linear properties. How do you define a nonlinear property? And I'll tell you the actual way to do it and what we're going to be doing today. So there's 2 ways to do it. If you actually click engineering data sources, I'm pretty sure we've gone through this before. You can look, there's different sort of generic alloys and stuff. Generally, you won't be using this if you're, analyzing something actually, because these alloys aren't really specific. They are just like general alloys to quickly run something. We're just going to be adding this aluminium alloy here. This was under general materials. And then what we're going to be, because this is way more convenient, we're going to go to general nonlinear, and we're going to add the aluminium alloy for nonlinear. So this actually has nonlinear properties to it. But what does nonlinear mean, right? Let's say you want to define your own nonlinear data set. So you can see we've defined aluminium alloy, nonlinear, and aluminium alloy. Let's say you want to define your own, nonlinear whatever, right? The way you could do it is if you go here, we click density, we click isotropic elasticity, all that is the same, but now you also go into plasticity, right? Because when you're past the linear region, you start seeing plasticity, which is like the effect of nonlinear, that you're permanently yielding the part and seeing plasticity. So there's different ways to define it. One which I've used before is the Hamburg-Osgood relationship. Now, this may mean nothing to you guys, that's fine, but it's generally a way, if you only have certain properties about, the strain, stress, Young's modulus, yield strength, and all that, this is a way to generate a nonlinear curve. Otherwise, does anyone have any thoughts on how else you could get this nonlinear curve? Let's say if you're analyzing something, any thoughts apart from this method? Yeah, a lookup table in MMPDS or just doing testing yourself. Nonlinear is really dependent on specific material types you're using. So a lot of this, like nonlinear properties, aren't really available online. So that's why you have to use methods like these to develop your own nonlinear tables. But yeah, you can also find it online or do your own testing, right? And if you did do that, you can go to nonlinear here. And then if you double click multilinear isotropic hardening, what you can see is here, you can add you can add data here in this column, where you can add the plastic strain and stress. So you would just add a table of values here. So, for some strain, like if you have 002 and let's say Pascal's, 100 to 1000, something like that, right? Of course, these aren't exact values, but you would define basically a curve, and then you would be able to define your nonlinear curve, and then ANSYS would use those properties. That does take a while, so we're not going to be doing that today, but I thought I'd show you how you would actually do it. But we're just going to be using the inbuilt aluminium alloy, which is in ANSYS, the nonlinear properties. Okay, so now if I double click model, get this to update.
Can I ask you a question?
Yes.
So ANSYS accepts true stress, true strain? Engineering stress strain curve.
Yes.
So the reason I mentioned or asked that question is because different software use different conventions. Yes. So some software may use true stress, true strain. And then the second part you need to understand is some data sources like MATWeb, MMPDS, some of the handbooks out there could use a very different, could use engineering or true stress strain curve.
Yeah.
So you have to be careful to make sure you're selecting the right curves and, or modify them so it's compatible with ANSYS.
Yeah, definitely. Yeah, always check it before like you input it. Yeah. Okay, so this should be pretty similar to what we've been doing all semester, but we're going to change the property. We're going to start with the aluminum alloy. So we're not doing the nonlinear to begin with, because I want you guys to see sort of how a nonlinear sim looks differently to a linear sim. We're going to add, I'm going to add the boundary conditions first. So it's just going to be a simple boundary condition here. We're going to fix both these ends. So these two ends are going to be fixed, and we're going to add a simple force on that hole. So maybe this is like a pin or something that's pulling on this surface. We're going to change this to applied by vector to applied by components. And so we want to apply it in the, and let's do -1. So let's put -2,000 pounds, right, to begin with. Right click, generate mesh. You can see the mesh is not that good as expected. We want to improve this. You can go to element quality, take a look at what it looks like. We have 4 mesh elements here. So similar to what we've been doing all semester. Let's improve that a bit. Change this to, so all I did there is I added a body sizing to improve that mesh. Okay, there's still a poor mesh in the center. What we're going to do is we're going to add a refinement on this hole. We're going to set it to 2, so we're refining it more. And on the mesh, we're also going to make sure we're in quadratic elements. Okay, so the mesh is improved. There's still some, some not great elements, but that's fine for now. Generally, this mesh is like pretty all right.
Well, that was the first order tetrahedron.
Oh, we're doing second order. It's a
If you plot that again, what is I'm seeing here?
This is element quality. ANSYS has
the second order, right?
Yeah.
And the reason I mentioned is if you use first order tetrahedrons, sometimes you will get results are very spotty.
Yeah.
So I recommend going to second order if your goal is to use tetrahedrons. Otherwise, I recommend using hexes. Sorry to interrupt you, Karan.
No, that's great. Yeah, definitely. Always, if you're doing TETs, use quads. Generally, good practice to use quads. Usually, only in like thermal analysis, I've had some issues with running linear elements. So maybe then use linear elements, but generally, quadratic elements or second order elements are always better. Okay, so we're going to run the linear model here. This is a linear model. So what you will expect to see is this model should run pretty quickly. So you can see it's almost done. That's expected, right? So we're going to right click and we're going to add deformation and we're going to add stress and then evaluate results. So let's look at this deformation. Okay, so as expected, we applied a load and it's deforming, right? Literally all that's happening here, F equals KX, right? Load and it deforms a certain amount, right? If you look at the stress, it's like 36 KSI. Okay, great. So now let's change this into nonlinear. Okay, so first thing we're going to do, of course, is, and definitely remember this is a very common mistake. You might go into like the analysis settings and turn on nonlinear, but if you haven't changed the material type to the nonlinear material, it will still be running linearly. So this is a very common mistake I've seen. So make sure you set it to nonlinear. Okay, now you've set it to nonlinear, that's not all, right? You have to go into analysis settings now as well, and you have to turn on large deflection. What this allows is basically like ANSYS sometimes will just say like, hey, okay, after we get to a certain deflection, we're just going to stop, which is not what happens in reality, right? Something is deflecting a lot, which is usually parts which are yielded. You need to allow the software to yield a lot as well. Okay, so we're going to run it again. That's pretty much it. You've defined the nonlinear properties. You've on analysis settings. You've turned on large deflections, and now you should be ready to run a nonlinear model. So let's click solve. See what we get. Okay, so you're going to see it ran pretty quickly, and we're getting pretty similar results. So what do you think is happening? Why are we getting like similar results, even though I've turned on nonlinear?
It's still in the linear.
Yes, it's still in the linear region. This is really important, and I did this on purpose. And the reason for this is because, some people might be like, okay, let's run this super high fidelity, nice nonlinear sim. Sometimes you don't need a nonlinear sim. You can run a linear sim, and a nonlinear sim is way more resource intensive. You have to go find more data. Sometimes it is okay to run a linear sim, right? So now let's go to let's go back. Let's change this back to aluminum alloy, and let's make this force 5,000 pounds, and we're going to turn off large deflection. So we're going back to running a linear model, but you'll see the stress should now be higher, but it will still treat it as if it's linear. Okay, so the stress is very high, 92 KSI, and the deformation, this is kind of.
So go back, show the stress.
Yeah.
Why was the stress high? Oh, because you applied bending. I'm trying to figure out the physics behind why the stress is higher away from the hole towards the edge compared to at the hole. You see what I'm saying?
Yeah, I see what you're saying.
It's not what I would have expected. You're bending, which way are you bending?
The constraints of these two are fixed, and the load is here.
Can you exaggerate the deformation? Is it bending like this?
Yeah, if you take a look. So it's kind of that like local surface. It's intention.
Okay. I don't understand why the stress is not high at the hole, but we can continue.
I wonder if it's because of a constraint. There's still some stress at the hole.
If you do the bending moment at the center is the highest, so the bending moment's biggest at the two surfaces. So it's the, like you're saying, the compressive intention stress.
Yeah, I think it does make sense. It's highest.
Are you bending it, are you bending the piece like this or like this?
The force is like purely like forward. Like if you're holding it like this, you're pushing it along here. So then,
Oh, you're pushing it this way? Okay, okay.
So like the top and bottom are getting stretched.
That's not bad. By the way, this is the kinds of questions I ask, even when I create a model, because we find simulations all the time where they're not making sense. So ask questions.
Yeah.
Of yourself, and other people should ask questions too. Sorry.
This is great additions. Yeah, sometimes you run a model and like, you might be like, oh, I have a pretty contour, but it might be completely wrong. That's the hard part with FBA. Anyone can, click buttons. The hard part is like figuring out if that model is correct. Okay, but now we're gonna try and run a nonlinear version. So hopefully I've convinced you that the linear one, looks pretty fine and nothing crazy is happening there. Let's turn on large deflection and see what happens. You can see it's solving, and if I have done everything correctly, it should take longer to solve. I think it is, yeah. So why do you guys think it's taking longer to solve that? Any thoughts?
It has to iterate.
Yeah, it's each time step, it gets a deformed shape, and then it reapplies the load. And then it gets another deformed shape, and then it reapplies the load. It's not linear, it keeps iterating through. So effectively you're running like, I don't know, like how many ever steps model, like you're running 20, 30 models actually. So each time it's running a model, it's iterating through. So that's why it's taking way longer. Hopefully the result's gonna be pretty cool. At least when I ran it, when I was practicing, it was cool. And there are other improvements you can make to this model. For example, you could make this a surface. It doesn't necessarily have to be a solid. Really, it should be a surface because it's a pretty thin beam. I'm doing this, quickly. We're showing you guys what nonlinear is. I do have a plate model as well. You'll see it's giving you some errors, right? It's saying your elements are becoming highly distorted. And
These
now
are very common errors.
look at what's happening here. The linear model showed us completely fine. It didn't look deformed at all. It looked completely fine. Whereas the highest stress was around here, which is why these elements are getting so distorted. So I think, and this is, by the way, this is true scale. This is actually what the deformation is. I'm not exaggerating it. If I exaggerate, it looks like that. I mean, it gets screwed. This is true scale. So let's run the animation. Does someone want to predict what it looks like? The animation. Any thoughts?
Slowly bends there.
You think it'll slowly get there? Okay. We can run and see.
I would like
Collapse? Okay. I'm gonna make it slow. So there's like some anticipation here. Okay, right. So the load, it's getting applied. Okay. And then bam, it just suddenly goes. It suddenly just deforms.
Yeah, you're doing load control, right? Not displacement control?
Yeah, this is just a force. And I'm fixing the ends. So yeah, no control. You can see it just suddenly goes. So what region of the stress strain curve is happening there?
strain hardening and necking that right after the high rates.
Yeah, it strain hardens and then it starts necking. So now for a given stress, it's deforming even more, right? Which is why it starts suddenly going, right? Because that's what necking is. And actually, if you go look at the graph here, you can see when the graph becomes nonlinear, which I think is very cool. Although I very much like FEA, so I might be a bit biased here. But yeah, you can see when it suddenly just becomes nonlinear. You can see here though, there is deformation happening, right? It's not like it's not deforming there, it's just linear. This region is linear. And then this critical moment at around like, what, 0.625, so around this low, or like this time step, it starts going nonlinear and then starts deforming more and more. So what do you think happens if we take this to the extreme? What if I keep adding more load?
Stop converging.
It'll stop converging, right? That's exactly it. And that's different to it breaking. So in most simulations, unless you define and you tell the simulation, hey, I want you to break, like show me you breaking, it's not gonna break. It's just gonna, at some point it's gonna asymptote like upwards and you're not gonna get a result. So it takes a while to run because it'll keep trying to run it. So I ran it before I came here and I'll show you guys. I think the sim is pretty cool of it's trying to break. It just like explodes. Any questions though? And then this is what the stress looks like. As you can see, yeah, of course, this region is high stress, but this is a very different stress graph to what we had in the linear region. It's a very important thing to look at, when you're running these types of sims. Even the stress changes like differently.
Karan, one question. How does it determine that those like time steps or simulation steps? I can see like for the linear, that's pretty, equally spaced, and then all of a sudden you're in the.
Yeah, there is a bunch of settings. Yeah, you can like change step controls and time controls. If you see, look, where it says autos time stepping, it says program control. So ANSYS will just detect when it starts going non-linear or starts deforming, not as it would expect. and then starts inputting more and more time steps there. It kind of knows. This is very different to if you're running a model in Abacus or FEMAP, you kind of have to define those. But in ANSYS, this is why people sometimes say ANSYS is like the easy fen, because like it kind of just does it for you. But yeah, that's how it determines it. But let's say, you know, you're in like another solver and you want to do it, you can turn off auto time stepping, and you can define your number of time steps, and you can define like how you want to define like at what spacing you want to define this. I'm guessing what it does is it detects when it goes nonlinear, and it's like, okay, I'm gonna have more.
Densifies it, then it relaxes.
Which is, I think, pretty cool. You can see there's only a few time steps here, and then bam, it goes. But yeah, this is the, so I modeled it as a surface because surfaces are more efficient to mesh. And when you're running a sim which is not converging, you don't want to sit there for 12 hours. So I ran a more efficient mesh here. I think it looks pretty cool. So let's run this. Oh, spoilers, no. But yeah, this goes, you can see it goes super non-linear here, but let's play it. Actually, we're gonna do it slower again. Okay, here, playing it. It's going, starts becoming non-linear, and then bam, it just breaks.
no.
Yeah, this is like not what you're meant to do. You're not meant to push it until it breaks. But the reason it breaks here and still is giving you results, like you can see here, it hasn't converged a result, right? Here even it says unconverged. This is because the pot broke, right? It can no longer just deform more. And so you can see it really tried to prevent it breaking, right? It started intensifying the amount of steps, and then it just really went, and then, you know, it kind of destroyed itself. But I think it's pretty cool. Like, even if ANSYS won't converge on a result, you can still get some stuff. You can see the stress is screwed. Like, you're not getting anything here. You can get the stress as it's happening, and then gone. Yeah.
So like pretty much like all materials with ductile fracture, would it make sense to always use a nonlinear approach rather than linear?
Yeah, so that's what I talked about before when we were doing the low force, right? When we were doing 2,000 pounds and we ran it between nonlinear and linear, you had the exact same result. But nonlinear is more computationally expensive.
Right.
It has to check for, am I past my stress strain curve? So it doesn't, I would say it's very good practice. Like if you have the resources and the time, yes, of course you should run nonlinear, because you never know. You might have a local stress concentration, or you might have something which you've missed, right? Which in a linear model, it'll just keep deforming linearly. But in a nonlinear model, the great thing is it does model these things, and it does, you know, model the plasticity. And another cool thing is, you know, let's say I stopped like somewhere here, like I took it here and I got like, you know, actually let's go to the other one. I got to this deformed shape, right? What you can do now is if you go into analysis settings and add another time step, let me just show you actually. So number of steps, let's put 2, right? And if you go to force, now there's 2 time steps, right? You can actually change this force, you know, and then let's do it the other way. You can change this force and then apply that force in the other direction, right? So you can see how the force changes over time. You can see how it's trying to like time step it. And then afterwards, you can apply a different force to it. So you can then get your nonlinear shape and then apply a different force, you know, if it's in a different loading condition, which is pretty neat. Yeah, that's all I wanted to cover. Hopefully that was cool. I think
That's
it's
pretty cool.
I think it's pretty
I've never seen done it this way to illustrate the instabilities that occur with nonlinear analyses,
Yeah.
the effects that you could have.
Yeah, you know, sometimes you might have like a perfect model, other times you have this, right? But still, this is very useful data. Like that's the thing, like you know here where, like what time step it broke, right? And you know this is like a broken model.
Do you have a question?
Can we run the one where you change the force?
It
'Cause
breaks, I've ran it, it breaks. It's actually like, it becomes very unstable at that point. So if you run it with this, I can show you, it will break. So.
Does it, if you just unload it normally, will it keep the plastic deformation?
Yeah, it does.
Oh, wow.
That's why the time step is useful. So imagine I didn't push it to 5,000. Let's say I pushed it to maybe like 3,500, and then I apply. You can even then apply a different load. You're gonna put a new force there and then apply a load somewhere else. And you keep the plastic model, and you can now apply that your new load to the plastic model. And I think there's a way in APDL to even extract the deformed shape, and then you can even pull that as like an STL and do CAD with it, which I think is very cool. That could be useful for some people, I'm sure. But it's a way to like take your plasticity and actually like, you know, now we're not only talking about like, okay, now we have, you know, we can put stuff into ANSYS. We can also extract things from ANSYS. We can do more CAD to it and then put it back in. Like, you know, everything in analysis kind of becomes coupled at some point, right? You'll maybe have like, you'll learn like fluids, you'll learn structures, but hopefully this is showing you that like, and when we get into more of these complicated analyses, I don't know the plural of that word, they'll become more coupled. Yeah, that answer your question.
Yeah, thank you.